So first, when we talk about fractions, we want to be able to identify numerators and denominators. So in a fraction, the top number is called the numerator, and the bottom number is called the denominator. And the bar in between we call a fraction bar. So in this fraction, 5 over 6, the numerator is 5, the denominator is 6. The 5 represents the number of parts we're considering. The 6 represents the number of equal parts in the whole. So a fraction is always part over whole. So the number of parts we're considering, number of equal parts in the whole. Numerator on top, denominator on the bottom. So an example. Identify the numerator and denominator of each fraction. Numerators on top, denominators on the bottom. Numerators on top, denominators on the bottom. Not too difficult. Now you may notice that the fraction bar looks awful similar to the division bar. So reviewing the division properties of 0 and 1, any number over itself is 1. 0 over any number is 0. Any number over 1 is itself. And any number divided by 0 is undefined. So let's simplify these fractions using the division rules. 9 over 9, a number over itself is 1. 6 over 6, a number over itself is 1. 0 over 1, any number over 1 is itself, or 0 over any number is 0, either way. The answer here is 0. D, 5 over 1, any number over 1 is itself, so this is 5. 13 over 0, anything divided by 0 is undefined. 13 over 1, anything over 1 is itself, so 13. In our next example, we're going to write a fraction to represent the shaded part of this figure. Let me shade the figure. Finish this example off. Okay. So there are 1, 2, 3, 4, 5, 6, 7 equal parts in the whole. So 7 is on the bottom of the fraction. The shaded parts are 2 of them. So 2/7. Write a fraction to represent the shaded part of this diagram. Three of the 10 equal parts are shaded. 3/10. Okay, draw a figure and then shade a part of it to represent the fraction 5/6. So let's say I just drew these, and let's say that they're all equal, because in order to draw a fraction out, we actually have to have equal parts. But I made 6 total equal parts, and I'm going to shade 1, 2, 3, 4, 5 of them. And that represents the fraction 5/6. It doesn't have to be a connected figure like this. So let's draw an unconnected one. Draw and shade a part of a figure to represent the fraction 7/11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've drawn 11 equal circles, and I'm going to shade 1, 2, 3, 4, 5, 6, 7 of them. 7/11. Of the 8 planets in our solar system, 5 are farther from the sun than Earth is. What fraction of the planets are farther from the sun than Earth is? Well, there are 8 total planets according to this problem, and 5 of them are farther from the sun than Earth is. 5/8. Okay, now let's talk about the difference between proper fractions, improper fractions, and mixed numbers. So a proper fraction is one whose numerator is less than the denominator. So for instance, 3/8 would be a proper fraction because the top is smaller than the bottom. On the other hand, 10/4 would be an improper fraction because the numerator is not less than the denominator. So it's greater than or equal to the denominator. So here also is a diagram of what 10/4 would look like. They're drawn as triangles here, but they're separated into 4 equal pieces apiece. So here's 4/4, and then another 4/4. And another 4/4 in the triangle, but then shaded are just 2 in this third triangle. Let me draw this out. So I'm representing fourths, by splitting these figures into 4 equal pieces apiece. And I need to draw enough of them to give myself 10/4. 1, 2, 3, 4, 5, 6, 7, 8. And so I need to draw one more triangle here in order to shade 9 and 10. But there's another way to think of 10/4 when it's drawn out like this. This is a whole piece, one whole. This is another whole piece, one whole. This is 1, 2 out of 1, 2, 3, 4. One plus 1 is 2, and 2/4. So 10/4 is the same as 2 and 2/4. And when we write it like 2 and 2/4, we have what is called a mixed number. So a mixed number has a whole number part and a fraction part. So in this example, we're going to identify each fraction, each number given, as a proper fraction, an improper fraction, or a mixed number. A, the top is smaller than the bottom, so it's proper. B, the top is not smaller than the bottom, it's equal, so it's improper, because the top is not smaller than the bottom. Same with C. The top is a bigger number than the bottom number. The numerator is greater than the denominator, so it's improper. D, 13/14. The numerator is smaller, so it's proper. E, 5 1/4. This is a mixed number. We have a whole number part and a fraction part. F, 100/49. The top number is bigger, so improper. Next, let's look at writing a mixed number as an improper fraction. So it's a 3-step process. We're going to first multiply the denominator of the fraction by the whole number. Then we're going to add the numerator. And then we're going to write it over the original denominator. Don't worry about writing this down. It's actually going to be a nice little picture I want you to draw. So for instance, when we have 5 2/7, we're going to multiply, then add, and keep it over 7. 7 times 5 is 35, plus 2 is 37. 37/7. B, we have 4 1/5. Remember, we're going to multiply, then add, and keep it over 5. 5 times 4 is 20, plus 1 is 21. So 21/5. So again, bottom to top, multiply, and add. Now let's look at writing an improper fraction as a mixed number or a whole number. So in order to write an improper fraction as a mixed number or a whole number, we're going to first divide the denominator into the numerator. So we're going to do top divided by bottom. Divide the denominator, the bottom number, into the numerator, the top number. So if we have numerator over denominator, numerator divided by denominator. Now, when we divide, the quotient is going to be our whole number part. But when we get a remainder, we're going to write the remainder over the denominator. So you'll see in this example, nine over 5 is 9 divided by 5. We're going to write the answer as a mixed number. 5 goes into 9 one time. 1 times 5 is 5. Subtract, we get a remainder of 4. We're going to put that remainder over the original denominator. 1 4/5. Let's divide for part B. 23 over 9 is 23 divided by 9. 9 goes into 23 twice. 2 times 9 is 18. 23 minus 18 is 5. So that's a remainder of 5. We're going to put the remainder over the denominator. 2 5/9. Let's now move into section 2.2 on factors and prime factorization. So in order to do a lot of math, you're going to have to be able to factor a number. So what that means is taking a number and finding two other numbers that multiply to give you the number. So for instance, if we had 63, we know 63 is 7 times 9. So 7 times 9 is a factorization of 63, because remember, the numbers that are multiplied together are called factors. So when we factor, we find factors. We find numbers that multiply together. So let's find all the factors of some numbers. $15. We want to find numbers that multiply together and give us 15. So 1 and 15, and 3 and 5. So 1, 3, 5, and 15. So what I did here was start running through numbers that have something times it to give us 15. So I started with 1. 1 times 15 is 15. 2 doesn't have anything, but 3 was 3 times 5. 4 didn't have anything, after 4 was 5, but we already had 5, which means we're kind of going back up the list. So once we start going back up, we know we're done. We've got them all. B, 7 is just 1 and 7. 1 times 7 is 7. 2 times nothing, 3 times nothing, 4 times nothing, 5 times nothing, 6 times nothing. Listing the factors of 24 should be fun. 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 times nothing, 6 times, well, we're back up the list. So 1, 2, 3, 4, 6, 8, 12, and 24. A and C, these lists that have multiple factors, we call these composite numbers. And B, 7, we're going to call that prime because its only factors were 1 and itself. So a prime number is a natural number that has exactly 2 factors, 1 and itself. These are numbers like 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Numbers that only are themselves times 1. A composite number is any number that's not prime. So, in this example, we have 3 numbers and we want to tell whether it's prime or composite, and then explain why. Well, how many factors do we have here? Is there anything besides itself times 1 that gives us 16? Absolutely, because 16 is 2 times 8, or 4 times 4. So this is composite, because it is not prime. 31. 31 is only 1 times 31, and that's it. So it's prime. 49 is 7 times 7, so it's composite. More than just itself times 1. The prime factorization of a number is the factorization in which all of the factors are prime numbers. So this might be more than just 2 numbers multiplied together. It could be a real long list. In fact, a lot of numbers are long lists because every whole number greater than 1, every whole number greater than 1 has exactly 1 prime factorization. So let's work on finding prime factorizations. Let's find the prime factorization of 30. So we're going to do this with a factor tree. We just need any 2 numbers that multiply together to give us 30. So how about 5 times 6? If it's prime, we can't branch it. 5 is prime. We can't branch it. But 6 is 2 times 3, both of which are prime, so we're done. 30 is 2 times 3 times 5. But here's the thing, these prime factorizations are unique. No matter how we split 30, maybe 15 times 2, 2 is prime. 15 is 3 times 5. There it is again. 2 times 3 times 5. We'll always end with the same prime factorization no matter how we get there. So let's do a prime factorization of 36. Six times 6. And 6 is 2 times 3. 2 and 3 are prime. Plenty of ways to get to this, but 2 times 2 times 3 times 3, written in exponential notation. 2 squared times 3 squared. 2 times 2 times 3 times 3. Again, just to show it doesn't matter. Maybe 18 times 2. And then 18, maybe that's 9 times 2. And then 9 is 3 times 3. From 18, maybe I did 6 and 3. And then 6 is 3 and 2. No matter how you break it up, you're going to get 2 2's and 2 3's here. 2 squared times 3 squared. When we're finding prime factorizations, when we're factoring in general, it's helpful to know a few divisibility tests. So a whole number is divisible by 2 if the last digit is divisible by 2. So if it ends with an even number. So it's divisible by 2 if it's even. And it's even if the last digit is even, 2, 4, 6, 8, 0. A number is divisible by 3 if the sum of its digits is divisible by 3. So for instance, 144 is divisible by 3 because 1 plus 4 plus 4 is 9, and 9 is divisible by 3. And a number is divisible by 5 if the last digit is 0 or 5. So let's write the prime factorization of 63. Well, 63 isn't even, but 6 plus 3 is 9, and 9 is divisible by 3, so we know 63 is divisible by 3. If we divide to find out what the other number is, 3 goes into 6 twice, 3 goes into 3 once. No remainder, just like we want. So 63 is 3 times 21. 21 is 3 times 7. So we end with primes. 3 times 3 times 7. That's 3 squared times 7. Because this is 3 times 3 times 7, and we would write 3 times 3 as 3 squared. Let's find the prime factorization of 45. 45 is 9 times 5. 9 is 3 times 3. So 3 times 3 times 5 is 3 squared times 5. We could have done this 15 times 3. And then 15 is 3 times 5. Either way, 3 times 3 times 5. Any way we break it up. Last one. Let's find the prime factorization of 72. 72 is 9 times 8. 9 is 3 times 3. 8 is 4 times 2. 4 is 2 times 2. So 2 times 2 times 2 times 3 times 3 is 2 cubed times 3 squared. So if you don't know your multiplication table, you're not going to be able to do this. No calculator in this course. Moving into section 2.3, finishing off lesson 10 here, with a discussion about simplest form of a fraction. Fractions that represent the same portion of a whole are called equivalent fractions. There are many equivalent forms of a fraction, and a special form is called the simplest form. It's written in simplest form, or lowest terms, when the numerator and denominator have no common factors other than 1. So first of all, what we mean by representing the same portion of the whole. Let's say these are two circles that I split in half. So if I shaded one of the halves, that'd be 1/2. But here, let's say before I shade it, I split it into 6 pieces. Then when I shade the half, I've actually shaded 1, 2, 3 pieces. So 1/2 and 3/6 represent the same portion of a whole. So they're called equivalent fractions. 3/6 though, 3 is 3 times 1, 6 is 3 times 2, 3 and 6 have a common factor of 3. 1 and 2 don't have any common factors outside of 1. 1 is just 1, 2 is 2 times 1. The only number they have in common as a factor is 1. This one would be in simplest form. So try to think of a number that these have in common. They're both even. So they're both divisible by 2. 10 is 2 times 5. 42, if we divide that by 2, we get 21. So we're going to cancel these 2's. It's going to leave us with 5 over 21. And 5 and 21 have no numbers in common. So 5 over 21 is simplest form. Nine 27ths. 9 and 27 have 9 in common. 9 times 1 is 9. 9 times 3 is 27. We can cancel those 9's and get 1 over 3. I want to look at this one more time, though. 9 over 27. Let's say you did 3 times 3 is 9, and 3 times 9 is 27. Then you cancel a 3 on the top and a 3 on the bottom, and you're left with 3 over 9. That can't be simplest form, though, because 3 and 9 still have something in common. 3 times 1 is 3. 3 times 3 is 9. Cancel the 3's to get us down to 1/3. So no matter how many times it takes, you're going to get to the correct answer of 1/3. C, we have 8 over 36. 8 is 4 times 2. 36 is 4 times 9. The 4's cancel, and we're left with 2/9. Another way of getting simplest form, kind of like this, but more meticulous. For instance, here, how did we know not to stop at 3/9? Well, we had to realize 3 and 9 had a factor in common. If we didn't realize that, we'd have said 3/9 was the answer and we'd have been wrong. This next method guarantees that we will get to simplest form without having to realize anything. And it's rewriting the numerator and the denominator with the prime factorization. So, let's write in simplest form. 50 over 22. We'll start there, because we need factor tree for 50. We need a factor tree for 22. 50 is 25 times 2. 25 is 5 times 5. So 50, and I'm going to leave this written out when we do it this way. So the top of this fraction is 2 times 5 times 5. I don't need exponential form here because I want to be able to see all of them. Also with 50, maybe 5 times 10, and then 10 would be 5 times 2. There's another way of getting 5 times 5 times 2. 22 is 2 times 11, both prime. So we see that this is now 2 times 5 times 5 over 2 times 11. The 2's cancel. 5 times 5 is left over, which is 25. 11 is left over on the bottom. 25 over 11 would be simplest form. Next up, 9 over 90. So we need a factor tree for 9. We need a factor tree for 90. 9 is 3 times 3. 90 is 9 times 10. 9 is 3 times 3. 10 is 2 times 5. So, rewriting this, 9 is 3 times 3. 90 is 2 times 3 times 3 times 5. The 3's cancel, both of them, because there's 2 on the top and 2 on the bottom. That leaves us with 2 times 5 is 10 on the bottom, and on the top there's nothing left. But wait, we can put times 1 there, no problem, which means there's a 1 left. When everything disappears, when everything cancels away, it leaves a 1, not a 0. 1/10. Next, 35 over 75. So we need a factor tree for 35, a factor tree for 75. 35 is 5 times 7. Both prime. 75 is 3 times 25. 25 is 5 times 5. So this is 5 times 7 over 3 times 5 times 5. 1 5 on the top cancels with 1 5 on the bottom. We're left with 7 on top, and 3 times 5 is 15 on the bottom. 7/15. Now, so we've learned 2 ways of doing simplest form. Let's use both of them to show that either way will work, whichever one we're more comfortable with. So first, we have 7 over 56. The first method would have us realize, hey, 7 is 7 times 1 and 56 is 7 times 8. Those 7's cancel, leaving us with 1/8. But we would have to realize 7 is a common factor. If we did the factor tree method, 7, well, that's already prime. 7 times 1. 56 is 7 times 8. 8 is 4 times 2. 4 is 2 times 2. So 7 over 56 is 1 times 7 over 2 times 2 times 2 times 7. The 7's cancel. We're left with 1 on the top. 2 times 2 is 4. 4 times 2 is 8. So either way, we get 1/8. Our next example asks us to determine whether 3/9 and 2/6 are equivalent. And one way to tell if two fractions are equivalent is that they would both reduce to the same fraction. If we put both of them in lowest terms, if they are the same, then they are equivalent fractions. 3 is 3 times 1, 9 is 3 times 3. The 3's cancel, 3/9 is 1/3. Or we can think of it as dividing top and bottom by 3. 3 divided by 3 is 1. 9 divided by 3 is 3. Two over 6. 2 is 2 times 1. 6 is 2 times 3. The 2's cancel. There again we have 1/3. So 3/9 and 2/6 are equivalent because they both reduce to 1/3. There's another way of telling if two fractions are equal, and that's using cross products. So let me rewrite this bigger. 6/24 and 2/8. So we want to tell if 6/24 and 2/8 are equivalent. Over an equal sign, we are allowed to multiply cross products. So this way we would have 6 times 8. This way we would have 24 times 2. 6 times 8 is 48. 24 times 2 is 48. They are equal. So yes, they are equivalent fractions. So let's do an example of this. Determine whether 2/5 and 4/11 are equivalent by cross multiplying. Well, 2 times 11, 5 times 4 is 22, and 20, they are not equal, so no, they are not equivalent fractions. We'll finish up here with this example that I have worked out. There are 5,280 feet in a mile. What fraction of a mile is represented by 2,640? Now we can divide the top and bottom by the same number repeatedly to get to our reduced form. And here, 2,640 and 5,280, wouldn't you know, they both have a factor of 2,640, except you wouldn't know because that's a difficult number. So this shows we can just quickly divide by 2,640 to get to our answer of 1/2. I'm here to show you that we don't have to realize that. We can take it one little step at a time. So what fraction of a mile, so what fraction of the 5,280 is 2,640? First of all, they both end in 0. So let's divide both by 10. That's going to give us 264 over 528. And now they're both even. So let's divide top and bottom by 2. Now notice, I'm not dividing everything by 10. I'm dividing the top by 10 and the bottom by 10. 10 over 10 is 1. I'm dividing by 1, which means I'm not changing anything. So make sure you don't write divided by 10 without writing it in both places. So if we divide top and bottom by 2, we're going to get 132 over 264. And both of those are still even. So let's divide by 2 again. $66 over 132. And guess what? They're both even, so let's divide by 2 again. 33 and 66. And around this point you can see, hey, this is 1/2. Maybe divide both by 11 maybe? Which gives us 3 over 6, and then divide both by 3. And get 1/2.
To remind you, if we had something like 24 over, let's keep it easy, 48. I said that you can do prime factorizations. 24 would be 2 times 2 times 2 times 3. 48 would be 2 times 2 times 2 times 2 times 3. And then we said we could cancel pairs. And we can only do this if it was all multiplication on the top, all multiplication on the bottom. There's nothing left on top, and we know because anything is itself times 1, there's really a 1 left on the top, and we're left with 1 over 2. The reason this works is because of how we're going to learn how to multiply fractions. Remember, anything over itself equals 1. So 2 over 2 equals 1. 3 over 3 equals 1. The rule for multiplying fractions is going to be that we just multiply across the top and multiply across the bottom. It's quite simple. Addition, subtraction, division, not so simple. But multiplication itself we can deal with. So really what's happening when we reduce this is we're getting 2 over 2 times 2 over 2 times 2 over 2 times 3 over 3 times 1 over 2. Oops. Times 1 over 2. And then this becomes 1 times 1 times 1 times 1 times 1/2, which is just 1/2. So that's what's at play here. Multiplying two fractions is exactly the same as multiplying across the top and multiplying across the bottom. This is an extreme example that I wanted to use to show why simplifying works. But we can just take something like 5/6 times 1/8. Multiply across the top, 5 times 1. Multiply across the bottom, 6 times 8. 5 times 1 is 5. 6 times 8 is 48. So this one is 5/48. We had 9/7 times 1/4. Multiply across the top. 9 times 1. Multiply across the bottom, 7 times 4. 9 times 1 is 9. 7 times 4 is 28. 9/28. Another one. 3/8 times 5 halves. 3 times 5 over 8 times 2. 15 over 16. Now, something's going to be a little bit different in the next one. And you might not be able to see what it is right away, but I'll point it out once we get to the answer. Multiply across the top, 3 times 4. Multiply across the bottom, 8 times 7. 3 times 4 is 12. 8 times 7 is 56. And right here, when we get 12 over 56, we notice they're both even. That's a divisibility rule for 2. Both of these share at least a factor of 2. We're going to have to reduce it. So how do we reduce? Prime factorizations will work. 12 is 2 times 2 times 3. 56 would be 2 times 2 times 2 times 7. Pair of 2's cancel, pair of 2's cancel. 3 over 2 times 7 would be 3/14. Or you can just start thinking of common factors. From 12 over 56, we know that 12 would be 2 times 6. 56 is 2 times something. How do we find out what that is? We divide. 56 divided by 2. 2 goes into 5 twice. 2 goes into 16 8 times. It'd be 2 times 28. That pair of 2's cancels. We're left with 6 over 28, but 6 is 2 times 3. 28 is 2 times 14. The pair of 2's cancel, and there's our 3 over 14. I'm going to show you an easier way than just multiplying across and multiplying across the top and multiplying across the bottom. This is called canceling. And it's called canceling because we start canceling common factors from the very beginning before we take that step of multiplying. How do we know when we can cancel? Well, 3/8 can't be reduced. 4/7 can't be reduced. But we should also look at anything from the top with anything from the bottom. And 4 over 8, that would be able to be reduced. 4/8 is 1/2. So what we're going to do is look for numbers on the top and on the bottom that both can be divided by the same number, and then we do it. 4 and 8 can both be divided by 4. 4 divided by 4 is 1. 8 divided by 4 is 2. And then those new numbers become what we have in those parts of the fraction. So really, this would be 3 times 1 over 2 times 7. 3 times 1 is 3. 2 times 7 is 14. When we cancel completely, we're not going to need to reduce. We got rid of all the common factors up front. What if you didn't notice that they're both divisible by 4? What if you just notice that they're both divisible by 2? That's okay. 4 divided by 2 is 2. 8 divided by 2 is 4. We just run our checks for cancellation again. Is there anything from the top that has a factor shared with something in the bottom? And yeah, 2 and 4, they can both be divided by 2 again. 2 divided by 2 is 1. 4 divided by 2 is 2. 3 times 1 is 3. 2 times 7 is 14. What if we canceled to get the 2 and the 4, but we didn't notice we can go further? Well, then we would end up with 3 times 2 over 4 times 7, which would be 6 over 28. And because we didn't cancel completely, we're still left with something that needs to be reduced. So you would still need to get it to 3/14. Let's look at another. Let's take a look at 15/5 times 6/5. Well, this is a problem that illustrates that canceling is very useful. Otherwise, we would have to do 15 times 6. We would have to do 5 times 5. We get 90 over 25, and we would have to reduce that. They both are divisible by 5. 5 times what is 90? 90 divided by 5. 5 goes into 9 once. 5 goes into 48 times. So it's 5 times 18 over 5 times 5. We get 18/5. And we can leave it in this form, even though it's an improper fraction. Why? Well, our rule is going to be if there's an improper fraction in the answer, you can leave it an improper fraction. Or sorry, if there's an improper fraction in the question, you can leave it improper in the answer. On the other hand, as we are going to see in the future, if there is a mixed number given in the problem, you have no choice. You have to put your answer in mixed number form if it turns out improper. But no mixed number here, we can just leave it 18/5. But there's got to be an easier way. I said canceling could work here, and then we wouldn't have to go through these big numbers. How would that work? And I am going to use cancellation where I can moving forward. 15 and 5 can both be divided by 5, whether we do this 15 and 5 or that 5. It doesn't matter which one. We need to do one of them. 15 divided by 5 is 3. 15 divided by 5 is 3. 5 divided by 5 is 1. Don't do both, though. One or the other. One of those 5s has to stay a 5 because 3 times 6 over 5 times 1, or 1 times 5, depending, is what gets us to our 18/5. As if DJ Khaled was here with us. Another one. 8 over 27 times 3 over 16. 8/27 can't be reduced. 3/16 can't be reduced. But 8 and 16 share some factors. 8 and 16 can both be divided by 8. 8 divided by 8 is 1. 16 divided by 8 is 2. 3 and 27 share some factors. One in particular, 3. 3 can be divided by 3. 3 divided by 3 is 1. 27 can be divided by 3. 27 divided by 3 is 9. You can see now why multiplication and division facts are very important. You need to know your multiplication tables. Make flashcards. There are websites that'll give you like flashcard games with the multiplication facts. We get 1 times 1 over 9 times 2. 1 times 1 is 1. 9 times 2 is 18. 1/18. If you don't cancel here, you would have to do 8 times 3 is 24. 27 times 16 is whatever that is, big number. And then you would have to reduce it all the way down to 1/18 to get the correct answer. The good news is, just because we're using fractions doesn't mean our 0 and 1 rules stop being what they were with whole numbers. So if we have 0 times 3/4, it doesn't matter that it's a fraction. 0 times anything is still 0. So don't let zeros fool you. Anything times 0 is still 0. 1/3 times 1/4. Is there anything to cancel here? Nope. On the top, 1 times 1. On the bottom, 3 times 4. Our answer is 1/12. From something with nice small numbers, unfortunately, to an example with very, very large numbers. 35 over 99 times 27 over 50. Now again, here you could do 35 times 27 is really big number. 99 times 50 is even bigger number. And then you would be responsible for reducing it all the way down to our correct answer. Or you can start looking for things to cancel. 35 over 99 doesn't reduce. 27 over 50 doesn't reduce. But 35 on the top and 50 on the bottom, as long as we can find 1 on the top and 1 on the bottom, we can cancel. They are both divisible by 5. 35 divided by 5 is 7. 50 divided by 5 is 10. We keep going. 27 and 99 are both divisible by 3, but they're also easier, both divisible by 9. 27 divided by 9 is 3. 99 divided by 9 is 11. 7 times 3 over 11 times 10 gives us our final answer. of 21 over 110. We got there relatively quickly with canceling. Otherwise, 35 times 27, 99 times 50, reduce, reduce, reduce until you get 21 over 110. What about if we had three fractions? Let's say we have 7/6 times 1/5 times 3/35. Well, we could go all the way across the top, 7 times 1 times 3, all the way across the bottom, 6 times 5 times 35. We would like to avoid that if we can. Those numbers would be very large and we would be responsible for reducing that fraction. So we look for anything on the top that shares a factor with anything on the bottom. I see a 7 on top. I see a 35 on the bottom. Why do I know that those are both divisible by 7? Because I know my multiplication tables. 7 divided by 7 is 1. 35 divided by 7 is 5. Anything else? The 3 on the top with the 6 on the bottom. 3 divided by 3 is 1. 6 divided by 3 is 2. And now we have 1 times 1 times 1 on the top. 2 times 5 times 5 on the bottom. 1 times 1 is 1 times 1 is 1. The bottom, 2 times 5 is 10 times 5 is 50. And this one would be 1/50th. Let's do another like this. 3 fractions. 1/5 times 7/2 times 1/3. Well, nothing cancels. The only thing of interest on the top is a 7, and nothing on the bottom can be divided by 7. So we have to go straight across the top. 1 times 7 times 1. Straight across the bottom. 5 times 2 times 3. If we can't cancel, we can't cancel. Got to do it. Anything times 1 is itself. The top is just 7. On the bottom, 5 times 2 is 10 times 3 is 30. 7/30. Next. Ooh, big numbers, scary numbers. 19 over 24 times 0 times 3 over 26. There's a 3 on the top and a 24 on the bottom we can cancel. But what else do we notice? It's all multiplication, and one of the factors is 0. Anything times 0 is 0. So this one is quite simply just 0.